High-dimensional scientific data, like soil channels from Monte Carlo simulations or droplet impacts on films, are complex, noisy, and hard to visualize. But what if we could compress them into meaningful 2D views, where similar patterns naturally group together? Here's how. We start with a semi-supervised autoencoder. First, we train an efficient NetV2 model on a small set of labeled data, just 2.5K images for soil, 7.2K for droplets, then generate pseudo-labels for the rest. Now comes the key. We don't just reconstruct the data. We add a clustering loss, a differentiable version of the silhouette score, to push similar data points closer in the latent space while keeping dissimilar ones apart. Then we project this enhanced latent space into 2D using UMAP, a superior alternative to TSNE or PCA for scientific data. The result? Marginal but meaningful improvements in cluster separation. The beta-VAE model outperforms the standard autoencoder, especially on the soil data, likely because its KL divergence term enforces a smoother, more structured latent space. But here's the catch. On the more complex droplet dataset, with 7 subtle classes and 160 times 224 images, the gains are smaller. The model struggles to preserve fine-grained differences during the deprojection. So yes, autoencoders with clustering or contrastive losses do improve visual interpretability, especially in structured, lower complexity scientific ensembles. But for the toughest data, we still need smarter architectures, better regularization, and smarter loss combinations.